to the video on motion in 3 space. Okay, so in this video we'll go over some more like physical applications to 3D motion of what we've learned so far, as far as like vector things. So first of all, the r of t that you see, this path is known as the I guess I'll just put equals, or I'll put an arrow. So this is thought of as the position vector. So this tells you where something is at a certain time, okay? And then the r prime of t is seen as, which could also be thought of as v of t, right? V arrow of t. So this is your velocity vector. Velocity vector. All right, and then kind of an offshoot of that is the magnitude of r prime of t, which we've learned is v of t, the scalar valued function, which is your speed, which is not a vector, okay? This is a scalar thing, so speed, okay, so that's the magnitude. And then our double prime of t is equal to a arrow of t, which is your acceleration vector. Acceleration, there we go, acceleration vector. All right, and something to bring up, and you've probably heard of this, even if you haven't taken a physics class, just your entire life maybe, but you've most likely heard of Newton, Isaac Newton, and his second law has to do with force and acceleration. So his second law says that F force of a certain position, force at a certain position is equal to m, the mass of whatever it is, times the acceleration, okay? Or this is also known as, this could also be rephrased as F of r of t is equal to m times r double prime of t, okay? So there's like one example of physical application. Another thing to keep in mind is that what we can do, how we can change between these given operations is the following. So we have our position vector, our velocity vector, and our acceleration vector. And to get from this one, from position to velocity, what we can do is just derive once. So d dt at once. And then you get to your velocity. And then to go from velocity to acceleration, the next step, all you have to do is the same thing. Take the derivative a second time. Okay? But going back is a little bit more complicated because then that involves initial conditions and whatnot, what have you, especially if you're trying to find a specific solution. But this is basically just going to be, so you can get v of t from the following formula. So we have the integral of a of t dt, and then plus whatever v naught is. So that means v at time equals 0. Okay, so this is like v at time equals 0. Okay, and then so that's how you get back to your original velocity function, or velocity vector. And then to get from v of t back to r of t, so from velocity to position, it's kind of like the same format. Now we just switch up the letters. So r of t is going to equal the integral of v of t dt plus r naught, whatever that original vector was. So this is also known as r at time equals 0. Okay? So that's kind of like a little roadmap on how you switch between your position, velocity, and acceleration. Okay? Another thing to note is that for uniform circular motion, then we have, so uniform, and meaning that it's going at, I believe, constant speed, perhaps not. Well, anyways, it just means something's moving in a circle, right? I think uniform just means it's a circle. So anyways, if something's moving in a circle, then we have what's called a centripetal acceleration. And we'll call this our a arrow of t. And this is going to equal negative r. And this looks like a w, but it's actually a Greek letter called omega. So omega squared times cosine omega t, comma, sine omega t. Sorry, that spilled over into the picture there. Okay, so this is, again, that's called omega. Kind of like omega-3 and omega-6, like fish oils. But anyways, omega. And the magnitude of this acceleration is going to be, here I'm just kind of deriving like some familiar formula that you might have seen if you've taken physics class before, and you might even know of it if you haven't taken physics class. But anyway, so this is going to turn into an r squared omega to the fourth, and then we have a cosine squared omega t plus sine squared omega t. So these are both going to be, these together is going to make a 1. And this is also square rooted because it's a magnitude, right? So what we're going to get is r omega squared. Okay, so this magnitude of our centripetal acceleration, centripetal meaning going toward the center. So anyways, this is going to be r omega squared, and omega, that stands for angular velocity. We don't need to go into details about that. Like I said, I'm just showing you the derivation of how we get to a certain formula. But you can replace angular velocity with v over r. So that's going to be squared. So we're going to end up with one of these is going to cancel with one of those down here. So what we get is v squared over r. And this v stands for speed, or like velocity. Or velocity in the sense that it's just speed. So I guess just speed. So anyways, this is the magnitude of our acceleration. Okay, so that was the final conclusion for that one. Like I said, I was just showing you the background behind why something's what, and this is for uniform circular motion. This acceleration equation holds true.
And I know you won't deceive me like the